The next transformations that we're going to look at are dilations. Now, dilation stretches the curve in one direction or the other. So first let's look at what happens when we stretch a curve vertically. Now, we always talk about the factor that we're going to stretch it by, and we define that factor as A. Now, if we're stretching vertically, it means that we're going to change the y parameter. So it makes sense that we're going to be replacing y with something. And in this case, we replace y with y over A, where A is our stretching factor. Now, this method will work for anything, let it be a circle or a function, anything at all. If your thing that you're stretching is actually a function though, you can also use this notation, where you'll say, if I had y equals f of x, then now I'm going to have y equals A, where A is your stretching factor, multiplied by f of x. And the reason this works is because if you take y equals f of x, and you replace y with y over A, it makes sense that if you want to rewrite it with y as the subject, you'll have to multiply both sides by A, and that's why the A comes over here and is multiplied by f of x. So you can think of it as putting your stretching factor out the front when you're stretching something vertically. Now, it could be a negative number, it could be a fraction, or it could be a whole number, and that'll change whether you're actually stretching to make it go further out, or actually compress it to come in, or even to flip it around, which we'll see shortly. So starting with some simple ones, we've got an example down here. Let's just leave this for a moment, we'll come back to it and have a look at how it works. Now let's take a simple graph parabola here, y equals x outside of x minus 2. Now you could rewrite that if you like as y equals x squared minus 2x, but it's quite nice to have it in factorised form here because it makes it much easier to sketch. We can tell it's x squared and it's a positive x squared, so it must be an upright parabola. And by letting y equal 0, we can see that it would have zeros, or x-intercepts, at x equals 0 and x equals 2. So I can graph it like this, and it's this black parabola here. And it's going through the points 0 and 2 on the x-axis. If I wanted to find the vertex here, it'd be easy to see that it's going to have an axis of symmetry right between the two intersects when x equals 1. If I sub 1 in here, I can see I have 1 multiplied by negative 1. It's going to be at 1, negative 1 there. Now, if I now apply this formula where I put my A out front, I've been asked here to stretch this parabola vertically by a factor of 3. So I can actually just put the 3 out the front and multiply that by the rest of my function. Now you'd have to be careful, because if I was given this parabola in this form, y equals x squared minus 2x, I'd need to be careful when I put the 3 out the front that I actually put the 3 out the front of some brackets and then the whole thing, because you need to multiply the whole function by that stretching factor. The reason I haven't had to do it here, I've just put the 3 out the front for my new stretched version of the function, is that I've already got something multiplied by something here. So if I multiply the whole thing by 3, I can really just pop the 3 out the front, so it's nice and simple. But just be aware that you'd have to do this if you had an expanded form. Alright, so I can very quickly and easily pop the 3 out the front here, and this will be my new stretched parabola. Now as I go to draw this, you'll see that it's very similar to this one. It's got zeros, or x-intercepts at 0 and 2 as well, in exactly the same two places. So if I graph it in red, it's going to come down like this. Now to get something of the shape of it, finding the coordinates of that vertex is a good idea. It will also have its axis of symmetry at x equals 1, but when I sub x equals 1 in here, I can see I've got 3 ones of 3 times negative 1. That'll give me negative 3. That explains why its vertex is down so much lower. Now if it's going down lower, it also explains the stretching. It's going to come up and be sort of skinnier up here as well, so it alters the shape. Now let's come back to this point here, which I haven't explained yet. You might want to pause the video to write it down. We talk about the axis of dilation. Now think about what you know about an axis. We normally talk about an axis of symmetry. So if I was to say to you, alright, I want you to flip something across the y-axis, we think of that as a horizontal flipping, don't we? Or if we flip it across the x-axis, we can think of it as a vertical flipping upside down. So it makes sense here that if we're going to talk about the axis of this dilation, then it's the axis that it's all happening around. Now we might be stretching vertically and changing the y values, because they'll change if you stretch something vertically or compress it vertically. But the axis of our action, in this case it's the x-axis, because that's the point that everything's enlarging or reducing around, isn't it? And the points that are actually on the x-axis, they won't move. You'll see here that the 2 points on our original curve, they didn't move when we stretched it, they're still in the same place. But all the other points get either closer or further away from the x-axis. And you could think of that as if we plotted any individual points on this original parabola. After the stretching, they've generally all got further, in this case, from the x-axis. But there are other cases where you can make a dilation with a factor that's a fraction, and that will compress it. Now we're going to do the opposite thing. We're going to stretch a curve horizontally now by a factor of A. So my notes here are similar, but I've changed some key words. Now if you're going to stretch something horizontally, it makes sense that the x values are going to change. So just as we did the other way around, we're going to replace x this time, because that's the values that will change. We'll replace them with x over A, where A is our stretching factor. Now, this will work every time. If your graph is also a function, you can use this method, or you can say, if I had y equals f of x, now I need to make y equals f of x over A. So just look for any x's that you've got in your function, replace them with x over whatever your stretching factor is, and then you can simplify or work with that as you need to. Now you'll see that the axis of dilation this time is the y-axis, because if we're stretching this way, then we've got the points that are actually on the y-axis won't move, but everything else either gets further away or closer to the y-axis. So I've given you the exact same curve this time, y equals x, x minus 2, we already graphed that. That was the black one. Let's just label that, that's black. Okay, and we graphed that already. We stretched it vertically and that made the red one. Now if we want to stretch it horizontally by a factor of 3, we're going to draw a blue graph in here for this new one. Now, how do we do it? Well, find the x's in the function, replace them with x over the factor which I've given you, which is 3 in this case. So instead of x, we'll have x over 3, and instead of x here, we'll have x over 3. Now, in this form, I can still see that it's a parabola, because I'm going to have the highest power of x being x squared. But I can also very easily see the x-intercepts. If I let y equal 0, then either x over 3 will be 0, in which case x is 0. So it goes through the origin here, just like the other two graphs did. Or x over 3 minus 2 would equal 0. And solving this little equation, I can see that x over 3 would be 2, which means that x would have to be 6. So coming along here, 2, 3, 4, 5, 6, it's going to go through this point here. So it's now got fatter, which makes sense, we've stretched it horizontally. Now, thinking about where our vertex would be on our parabola, if we've got intercepts at 0 and 6, the axis of symmetry would be x equals 3. So summing that in, just to see what sort of y value I'm going to have, 3 over 3, well that would be 1, multiplied by 3 over 3, that's 1, minus 2, minus 1. So you'll see what actually happens with this blue parabola that we're going to make is if we take the original black one, the one that we've now stretched horizontally, it had its vertex as a y value of minus 1, so does our new parabola, but now it's at 3 minus 1 because it's stretched along. So I can draw this one like this, and it's going to come up like this somehow. There's a big, wide, fat parabola, and it's got its axis of symmetry here at x equals 3. Now, the thing that's the same on both when we stretched vertically and stretched horizontally is we ended up with a point that was exactly the same on all 3 parabolas. So now we can label this one y equals x over 3, x over 3 minus 2. And we can see what effect that had on making this parabola really wide.